Now we discuss the application of the work-energy theorem in the case where external non-conservative forces do net work. In this case, the work-energy theorem takes the form WNC equals EF minus E0. In many cases, we think of the net non-conservative force as something dissipative, such as friction or air resistance. In this case, WNC is negative, and some mechanical energy is lost in the process since the final energy must be less than the initial energy. But another form of a non-conservative force is that of an onboard propulsion system, such as a rocket engine or the engine of a car, in which one form of energy is converted to mechanical energy that can be added or subtracted from the initial energy. In this case, WNC can be positive or negative. This is conceptually illustrated in the case of a car going up a hill. If the car started its ascent at a certain speed, i.e. with some initial kinetic energy, and the engine was turned off, the car would coast up the hill until all of its kinetic energy was transformed into gravitational potential energy. At that point, it would start to roll backwards unless the driver hit the brakes. On the other hand, you could imagine that, with the engine running, the driver could maintain the speed of the car as it climbed the hill, thereby keeping its kinetic energy constant. However, as it climbs, it constantly gains gravitational potential energy. In fact, since the kinetic energy doesn't change, the positive work done by the non-conservative force is equal to the change in gravitational potential energy. In all, in this case, the total energy is not conserved and increases. In summary, when non-conservative forces do net work on an object, the work-energy theorem takes the form WNC equals EF minus E0. WNC can be negative, as in the case of friction that opposes the motion, or positive, as in the case of propulsive forces.